So thanks very much for the opportunity to talk today. I'm going to, as the title says, talk about equilibrium models in solar physics. I'll be mainly talking about MHD models, although at the beginning I will mention as examples some kinetic stuff that we did over the past few years. Also, I've not done the work that I will speak on my own, so I have a reasonably long list of collaborators there. I'm pretty certain it's incomplete. Lots of them are former or current PhD students, postdocs, and international collaborators. So thanks to all of the people who've worked with me on that over the past years. Right, so let's start quite simply and just look at force balance. I'm pretty certain you're all aware of the MHD equations. So most of the time we'll be talking about MHD, as I said, and force balance equation that we would use there, I've highlighted here in light green. Of course, if we do MHD, the prime force that we add to hydrodynamics is the Lorentz force, J cross B force, which always acts perpendicular to the magnetic field. I've made a little cartoon here, obviously hand-drawn, which sort of indicates the forces that we have there. Then we might have plasma pressure, and we of course have a force acting into the negative direction of the pressure gradient. And then we might, if either the scale heights are larger than the smaller than system size, or if we go further out into the corona, we might have to include the gravitational force. And of course, you have to complement that for equilibria with Ampere's law and divergence of B equal to 0. And you might have other equations depending on what kind of situation you have, like an equation of state, potentially an energy equation and things like that. Now, I should say I've only put the MHD equations down here, or the MHS equations, magnetohydrostatic equations. If we have a kinetic situation, the pressure might not be a scalar, but it usually is a tensor. So you would have the divergence of a pressure tensor. You would also derive the force balance equation from an underlying kinetic equation, for example, a collisionless theory, like I will discuss as examples on the first two slides. After this, you would have the Vlasov equation plus Maxwell's equations as appropriate. Okay, so that's the situation we have. We're trying to solve sort of a set of equations like that. I'll try to keep the math to a minimum if anyone's scared that the first slide already has mathematics in. So one application of plasma equilibria would be to use them as initial conditions for investigations into other things like time-dependent phenomena, waves, instabilities, nonlinear behavior, and so on. And I've sort of present on this slide one example from my work, which is sort of taken from kinetic theory. So on the right-hand side, and you can ignore actually this time-dependent vertical line which goes to there, which just highlights some properties of this equilibrium. The important bit is this here. That's the magnetic field structure. So this is a hyperbolic tangent magnetic field. So maybe before I go into that in more detail, the coordinate system is that the x-axis is this way, the z-axis is across the current sheet, so you have a current in the middle here, which goes into the y direction, okay? So this is a hyperbolic tangent profile, and this is normally known as a Harris sheet, but this is special because it also has what is called a guide field. Solar physics, we would call it shear field, maybe into the board, so into the y direction. There's no initial magnetic field into the z direction, and that makes this current sheet force free, which means that the pressure here, it is one component of the pressure tensor because it's kinetic, is constant, and b squared is constant, and that makes the whole thing in 1D force free. And we've done quite some work over the past, I don't know, something like probably nearly 15 years now on things like that under various circumstances with various conditions. And the task there is usually to find the distribution function, particle distribution function, which underlies these structures and makes them self-consistent as equilibria. But we've also sort of done time-dependent investigations. That's exactly what the title says, that we've used this particular kinetic equilibrium as an initial condition for PIC simulations, which you see a movie of on the right-hand side. I won't go into much more detail there. So the particular property of this simulation is that it starts with what is called guide field reconnection. And because you're moving in more and more sort of flux from the side, which doesn't have any guide field in, you have a transition between guide field reconnection initially and non-guide field reconnection later on, which has different properties. Okay, another application, and again, I've just sort of taken an example from my own work here. I could have picked many different examples, of course, from also other people's work, is to use equilibrium models for direct modeling of observed magnetic field and plasma structures, either in the corona or, of course, Earth magnetosphere and so on. So this particular example, and this is a pretty busy slide, so let me talk you through that. If you concentrate on the bottom row in both these figures here, that's probably easier to explain what it shows. So these on the left hand side here, these four figures are sort of generated by data taken from the Artemis mission, and that's published in papers by Anton Artemyev and co-workers in 2019. And this is a collaboration actually with Anton Artemyev and Ivan Vasko, plus Oliver Ellison, that we've done sort of a couple of years ago. And the task here was actually to use the current sheet models that I've discussed on the previous slide to model some of the properties that these guys have found for tangential discontinuity / current sheets in the solar wind at about 1 AU with this mission. And I will not go into the magnetic field structure, but one particular property that these observations have is that the plasma beta, which is shown here, is nearly constant across these current sheets. But that one sees a notable and systematic variation of the temperature and the density, which seems to be in opposite directions. And of course, then the pressure can be, as a product of those two, can be nearly constant. So this indicates that these structures might be force-free in a sense, although they have a plasma beta which is much larger than 1.5 in this case on average. And the models that I showed, the current sheet models that I showed on the previous slide, actually have exactly that property. You can see that this is kind of a representation of magnetic field against magnetic field. So that looks similar. This is the current density across the current sheet. That looks similar. We have a constant plasma beta, but our density and temperature are also constant in these simple models that we've published a long time ago. So there's no asymmetry there. But based on an idea that I think Ivan had, we could sort of come up with an improved model where you tweak the distribution functions a little bit, and you get the same variation or similar variation, at least across the current sheet, of the density and the temperature, and that can maybe serve as a first order model for these structures at a kinetic level. So that just as one example of applying equilibrium models to data, so to say. I mean, whether that is the correct model remains to be seen, and whether an equilibrium model actually explains everything one observes is another question, but at least we were able to sort of come up with a model which has the same characteristics there. Okay, let's move on and come to the main part of the talk, which is applying equilibrium models to magnetic field extrapolation. And just although it's probably not necessary, remind the audience of the importance of the magnetic field as a major factor in structuring solar corona, and I've just taken this old trace image here of coronal loops, where we believe that the emission structure is of course shaped by the underlying magnetic field, which should have a similar structure. We know that the coronal plasma is nearly ideal, and the plasma beta is usually smaller than 1. And that is one of the reasons, this nearly ideal condition why we think that the plasma is directly linked to the magnetic field, and that what we observe highlights traces out the magnetic field lines, or the structure of the magnetic field. On the other hand, we also know, because the magnetic field is one of the dominant factors in the coronal structure, that is important for analyzing and interpreting observations, but also to inform theoretical investigations. So that kind of links into what I've said before in the previous two points in the previous 2 slides. Okay, so how would we determine the coronal magnetic field? And I mean, while methods are being developed to measure the magnetic field directly in the corona, which is difficult, accurate measurements of the B vector are still routinely only possible in the lower atmospheric layer. So we're still relying on extrapolation methods to determine coronal magnetic field models from mainly photospheric, now sometimes chromospheric observations. And to do that, we use MHD equilibria. So that links to the title of my talk. And just as an example of such a method, I've shown on the right-hand side a figure from a paper by Thomas Wiegelmann and et al., where one of the et al.'s is myself, where we compare 3 different extrapolation methods. So figure A is a potential field model, figure B and C are kind of MHS models. And the data that we use there are from the Sunrise balloon mission and the IMAX instrument on that balloon mission. I think that was the first flight in 2009. I think the Max Planck Institute are currently preparing for the 3rd flight sometime in the near future, if I'm informed correctly. And this is part of what I'm going to talk about, not this particular paper, but sort of the underlying equilibrium models. Okay, just a brief summary of extrapolation in general. There's of course a large variety of methods that we can use. So I'll mainly concentrate on analytical methods. I mean, we're still using potential field models. I myself do that occasionally with PhD students and so on. Then of course there's linear force-free models. Then if you go over to nonlinear force-free models or MHS models, you usually, magnetohydrostatic models, you usually use numerical methods to do that, because as the word nonlinear force-free says, it's a very nonlinear problem, and there are no analytical solutions that can be used there available to do any modeling. For the MHS, that's slightly different. That's largely the topic of my talk. And of course, as I already alluded to, that there's the linear extrapolation method. So that's basically potential linear force-free, and partially also these MHS models versus nonlinear. Then of course, we have either local extrapolation, which was what I showed on the previous slide, where you cut out a part of the solar surface or part of the surface plus corona and model that part on its own. Or you can do global models where you model the full sun. Then of course, it depends on what kind of boundary conditions you impose, whether you just impose the normal magnetic field or you have a vector magnetic field that you impose, which is usually done for nonlinear force-free methods. And then is it based on kind of instantaneous fields, which are the data taken at a specific time, or are you doing long-term models which include sort of magnetic flux transport on the surface? That's, for example, what people like my colleague here in St. Andrews, Duncan Mackay, or Anthony Yates in Durham, or Karen Mayer in Dundee do. And I've picked one example of that on the right-hand side from a recent paper by Karen Duncan and other collaborators, where they've used one of these models, which is shown on the right-hand side there, to compare with EOV data from the SWAP instrument on the Proba 2 mission, which is shown on the left-hand side there. But that's something I wasn't involved in. So just to show what different types of modeling are possible. Okay, to sort of start the tour de force or continue it through models. So global potential field models are still kind of one of the common tools used, and that is of course because they're numerically cheap to do. They're very easy to understand in terms of their mathematics. We usually use source surface models, so you have an inner spherical boundary where you impose the magnetic field, the measured magnetic field component, and you have an outer boundary, which is usually somewhere at between 2.5 and 3 solar radii, where you impose the condition that the magnetic field becomes radial. And then you can calculate by separation of variables, basically an expansion in spherical harmonics. And if you do that, you get pictures. You can get pictures like the ones on the right, which have been taken from a paper by Sarah Platten and my colleague Claire Parnell, plus I think a few other people. Again, I wasn't involved in that. I was involved later just as internal examiner for Sarah's PhD. But what you can see there are magnetic field lines, but these are particular magnetic field lines. They are basically magnetic field lines which lie in separatrix surfaces which occur in these models. And the two figures are basically solar minimum at the top and solar maximum at the bottom. And one can see the green lines, which are best visible at the top. These are field lines which come from the heliospheric current sheet. So that's basically where the radial magnetic field is 0 on the outer boundary. And you can see that this closed surface, which looks a bit like a shell or something like that. Whereas you see the complex nature of the magnetic field, even in these potential field models during solar maximum at the bottom. And you can investigate then sort of topological features. I think the colored blobs are basically open flux regions, which are kind of labeled there. So this gives an example of how potential field models can be used. But obviously they have their limitations. But one could still, I think, if one knows the limitations, is aware of them, and doesn't overstretch the importance of certain features, then one can use global potential field models for very well for different purposes. Okay, and another example that I wanted to show for nonlinear force-free extrapolations and what we can do with them. So here on the right-hand side, I show an example again of a work that I wasn't involved in by Klein et al. 2018. So here one uses, of course, that the corona, at least lower corona, is to a large extent force-free because the plasma beta, the ratio of the pressure, plasma pressure to the magnetic pressure is much smaller than 1 usually. Then one finds that the current density, of course, is in the magnetic field direction, which is usually expressed as J being alpha B, where alpha is not usually spatially constant. And if you do this in 3D, then you usually require numerical methods to do this. And that's not straightforward. And many different methods have been used and proposed. So Grut-Rubin in the UK, for example, maybe not exclusively, but Stéphane Régnier in Northumbria has worked on Grut-Rubin method for a long time. There's MHD relaxation, magnetofrictional methods, and then optimization, which is something that Thomas Wiegelmann has been using in lots of the collaborations that we've done. And a review of all the methods and so on can be found in the living review by Wiegelmann and Sakurai, which has just been, I think, updated in 2021. So on the right-hand side, you see one of the potential usages of nonlinear force-free extrapolations, where these guys have looked at the change of the magnetic field from before a flare to after a flare, and how it links up with observed emissions there. Or, of course, in the literature. Okay, so what I would like to concentrate on is sort of magnetohydrostatic methods for extrapolation, or MHS. And the background there is that, of course, while the corona is largely force-free, at least in the lower parts, we measure and extrapolate from data which are taken in layers of the solar atmosphere, which are not necessarily force-free. Would there be any problem with that, that we actually use a force-free approximation in regions where, even though small, the force-free approximation is actually not really that valid, and this has become more of a problem since the magnetograms that we use to extrapolate and as input data have become much higher in resolution. So, for example, the IMAX data, if I remember correctly, have a pixel size of about 40 kilometers, which of course is much smaller than the height of the chromosphere. If one wants to make use of all the data, does one have to sort of think about resolving this non-force-free layer? And there's work on numerical codes for that. I've listed a few papers here. I've just come across one which I think has been submitted to Journal of Computational Physics by Matthews et al., which I think is more on global extrapolations, but looks very interesting. And Thomas Wiegelmann has, of course, tried to, together with his postdoc Zhu, has tried to extend the optimization method to MHS as well, and Grad-Rubin-like methods have also been tried, and so on. Relaxation, I think, has also been put forward there, and this is certainly an incomplete list there. What I've been interested in is whether there might be any kind of analytical shortcut, so something which might be reasonably cheap to calculate, but still allows people who wanted to have a quick look what changes if one includes other forces, to have a rough and ready but sufficiently accurate or satisfying quick look thing, whether if one has a high resolution magnetogram and wanted to include these non-force-free layers, whether anything changes radically or not. Okay, so that's what I'm going to talk about in the next minutes or so. Okay, so just as a background, here's one slide about how we go about calculating this analytic MHS equilibria. So this is based on a lot of work which has been done by B.C. Lowe and others in the 1980s and 90s largely. And we include both a gravitational force and pressure. And the problem always when you want to make analytical progress is that you have to make compromises to some extent about what you assume about the physics. And of course, one of the things, and that goes for this particular type of model in the same way as it goes for potential field models, is that one has to be aware of the limitations of these solutions then in the end. So one shouldn't sort of, again, overinterpret what one finds. On the other hand, they can still have great value if one, as I said, wants to have a quick look at what additional forces might change in the extrapolation. So let me briefly talk you through the important parts here without going too deeply into the mathematics. So we assume here that we do a local approximation. We can also do this globally for spherical coordinates, but here we use Cartesian. So the Z coordinate here will be kind of down, upwards from the solar surface. So gravitational force will be assumed to be constant, and downwards with a constant gravitational acceleration, small g. And then we assume we have magnetic field B, which is sort of on the right-hand side here. So that's the gravitational acceleration. And then we make an assumption about the current density. And that's how we get our analytical solutions. The assumption is that the current density consists of two parts. And that's in this green box here. So we have this sort of weird looking part, which is perpendicular to the gravitational force. So that's indicated by this vector here, right? So that's always perpendicular to the gravitational force. And that's kind of the key assumption which goes into these models. And we have the gradient of the magnetic field in the Z direction here, and the free function which depends on the height. So this, unfortunately, is one of the assumptions we need to make. I will not go into why this is possible, why this is necessary, but the essence is it's necessary to make any analytical progress which allows you to do this. So that's the limitation here. And then you can add a constant alpha linear force-free part here, which is basically along the magnetic field direction. Okay, so this is parallel to the magnetic field. This is not perpendicular to the magnetic field, I have to point out. So this is only perpendicular to the gravitational force, and it will have components which are also parallel to the magnetic field, but it will have also components which are perpendicular to the magnetic field. Okay, so when I use the word perpendicular in the future, it might have two meanings, and I think I'm not always clear, even myself, whether I mean perpendicular to the gravitational field. I usually will mean perpendicular to the magnetic field. But this free function f of z here, that controls how large the perpendicular current density is in this model. And that basically controls how large the effect of the non-force-free components are. Okay, so that's the important point here that I would like to bear in mind. Because it's a free function, that's something we choose in the modeling effort. And depending on what you choose, you get different results. So just two examples of things that have been done before. So a long time ago, Gordon Petrie, when he was my PhD student, he played around with these things and investigated theoretically. And in his thesis, he and this paper in 2000, we used basically that f of z is constant. That's the simplest choice you can have. And mathematically, what you then change, if you change f of z, is how the magnetic field depends on the z coordinate. So on the vertical coordinate, that's what you change. You basically get an infinite series of solutions, and the coefficients in these solutions are dependent on z. And in this particular case, you get exponential functions there. So with different drop-off scale heights, and they're all summed up together with sort of whatever happens in the x and y direction. So that's a very simple thing, and you can sum that up. And I'm just showing the difference between a potential field here. That's kind of an artificial sort of magnetic loop that Gordon has dealt with in his thesis. And this is what happens if you add these currents. So it's slightly depressed field lines. I can't remember the exact details of that. Actually, would have to look at the thesis again. But what happens if you add these extra fields? Now, Lowe already in 1991, in one of his papers, a series of 6, 7, or 8 papers on these things, plus extra papers earlier, which do not belong to the series. So he experimented with f of z being an exponential function. And that, of course, allows you to control with these parameters a, b, and this height L, allows you to control when the effects of these extra forces, pressure gradient and gravity, when they drop off and how they drop off with height and how fast they drop off. So you can basically go from something which is magnetohydrostatic to something which is linear force free at a certain height. And that's what we've used in this 2015 paper, of which I showed the A, B, C things before. And this is shown on the right-hand side here. So this is what you get if you do a potential field extrapolation of these data, sunrise IMX data. And this is if you do an MHS model with sort of fitted parameters that we used. And you see that the connectivity changes quite dramatically, especially for these ones. It would also do similar things if you did a nonlinear force-free extrapolation, but we haven't done that as a comparison. Various people have used that for other things, like Guillaume Olanier has used that in the 1990s to model, I think, prominence channels, if I remember correctly. Here, instead of these exponential functions that you get for the Z-dependence, you get Bessel functions. Not the nice Bessel functions that you usually have with integer index. You usually get Bessel functions with sort of irrational indices, which are not so nice and not so easy to control numerically. So that is better than that in terms of controlling these non. That's the essential message here that I would like to take you away from this right-hand side. So what we've tried to do is ask the question, really what Thomas and I have tried to do is, can we control these non-force-free terms even more? Or in other words, can we control the current density even more, as I displayed it sort of 2 or 3 slides ago? Or rephrasing that, can we choose an f of z, which is the function which allows that, which allows us more control over what the models do? And what we come up with is kind of highlighted on the right-hand side here in this figure. So what we have, so this is z here on the bottom axis, and this is f of z. And what we've done is a kind of hyperbolic tangent function, which has various parameters, which I'll explain in a second. So this drops off over a certain distance, which we've called delta z. The height where it drops off, we've called z naught, and then the 2 parameters a and b, which control a, basically what the amplitude is here, you know, where you start at z equals 0. So how large is your current density in some sense at the point where you impose the boundary conditions, and then how far does f of z drop off? So if you wanted to call give these parameters certain names, you could call a the amplitude parameter, b is what I've internally always called the switch off parameter, z naught is the height of the switch off, although it's not totally switched off, and delta z is the width of the switch off. So just to remark, you can either switch off the currents totally, asymptotically at least, or you can actually have a b which is not equal to 1 in this function, and you can keep your non-force-free currents and effects at a finite but very small and controllable level. We haven't done that yet. We haven't looked into that, but that's something that we might want to investigate in the future. Now, the problem with this is that with such a reasonably complicated function, of course, you get complicated z dependence, and I will not show you what it looks like, but I just mentioned the words hypergeometric functions that you get in the z direction. And you have to sum over them, and where there are sort of codes which can calculate hypergeometric functions, there's none in IDL as far as I'm aware. So I had to find something on the web which works. The other problem is that because we're working to some extent, not just in this transitional region, but also where we're basically at 0 and more or less at 1, we get very close to the singularities in the hypergeometric differential equation, which makes the behavior of the functions not so nice, and one has to do all kinds of tricks to sort of make it work. If anyone's interested in the details, there's a paper that we published in 2019 in Solar Physics about this. And actually what I show you is largely from that paper. Okay, so what do the magnetic fields look like? Here, I will only show, I mean, we're working on applying this to data. We haven't done that yet, but mainly because of the difficulties with sort of the hypergeometric functions, but I'll show you something which is derived from a toy magnetogram, which is roughly similar to what Gordon Petrie has done in his thesis. So we're doing basically one magnetic loop, but in a periodic way, so that we can fully analyze in the X and the Y direction. And I'm just showing the kind of BZ profile on the bottom surface. So we have a positive polarity and a negative polarity blob. And if anyone's interested in the mathematical shape, I've written it down here. It's basically like a periodic, two periodic Gaussians, if you want to call it that. This actually has been nicked from statistics. It's called the von Mises distribution there, but you know, it's nice because you can control the shape and you can get away with very few Fourier modes if you wanted to analyze that in the X and the Y direction. That was the only reason. So it's practicality rather than anything else. Okay, and if we calculate the magnetic field, there's the box with the parameters that we've used there, and there's various animations should be running. So this is one where we don't have any parallel extra parallel current. So alpha is 0. On the right hand side, there's one where alpha is set to 0.5. And what is being done here is that this amplitude parameter A is ramped up from 0 in both cases. And this is a side view here. So Z0 is in the middle here. So that's where the Z0 is, where this transition from non-force free lower down to force free happens. And you can see when I ramp up the non-force free amplitude parameter, the field lines in this non-force free regions get a lot steeper, and you get something which I wouldn't call it a canopy, but it basically sort of, you see that the currents have an effect there, albeit in a you know, not outrageously large effect. See it a bit more here if you have an extra alpha, but definitely that there is an effect there. What happens if we have, you know, obviously this is a very simple structure, but if you had a more complicated one, you might not even see this effect directly. So I have two stills here so that you can see more easily, you know, what the difference is on a larger scale as well. If I go back and forth, so you see the difference in the lower layer. So this is over the whole box. If I go up to sort of the highest A that we could do, because there is a limit on the A before things get singular. Sorry, that's going backwards. And this is kind of what we did. So the height here is, I've chosen a height in sort of the normalized coordinates, which would be roughly sort of transition region height and a kind of transition region width. Although I have to say, you know, nothing ties the magnetic field model to actually the atmospheric model that you impose in addition to what you do. So you don't have to have the same values there. Okay, one other thing that you get out of these models is the pressure and the density, and you have basically a pressure and the density which consist of a stratified background pressure and a stratified background density, which are connected to each other, plus a variation delta P and delta rho, which, I mean, I've given the formula here, but you don't need to look at that, but which sort of modify the stratified atmosphere actually in 3D. And I've tried to highlight what happens in this model with these figures here for the pressure. So this is below the switch off, so where the currents flow, and you see the density is kind of changed here where the loop is, and not much elsewhere. But as soon as you switch off the extra currents, you basically have a flat pressure surface here. So this is the isosurface of pressure, I should say. So the z-axis here is not z, it's actually pressure. Whereas above the switch off here, because we've switched it off completely, the pressure would be basically flat. So you had a hydrostatic atmosphere there. And the same goes for the density. You have even sort of higher sort of change of density and below the switch off, and above the switch off, everything's nice and stratified. One thing, and that is one of the things that one has to be aware of when one uses models like that, you can only have a background pressure which drops off with height. You cannot have anything which at any point starts to, at least temporarily, increase with height, because the derivative of the background pressure gives rise to the background density, or the negative derivative rather. And the background density has to be positive, otherwise you run into problems with negative density. And the pressure always has to be bigger than sort of this delta P, which is also always negative if f of z is positive, which is, there are reasons for having that, because otherwise the forces point into the wrong direction. So these are some of the limitations that one has to be aware of when one uses models like that. Okay, right. So I just wanted to touch upon towards the end on two other things that we've done. So one of the things that one can do with models of the same nature, and I've mentioned that we can do the same things in spherical coordinates, and you could apply that not only to the sun globally, but also to other stars. And on the left-hand side is an effort that was led by David McTaggart, and it was Scott Gregory, who was at St Andrews at that time. I think it's on D now. Who's led that effort and applied it to magnetic field data from a star called, what is it, GJ? I always get that the wrong way around, GJ182. That's a rotating star. We did this without rotations, it's just spherical coordinate static. My PhD student Nasser Al-Salti has tried to incorporate sort of rotation into this model. So that's possible. The problem is that if you do that, and that's shown on the right-hand side, that's a model with a kind of artificial surface magnetic field where you have a 3D sort of tilted and displaced dipole in the middle. Well, not in the middle actually, because it's displaced, but inside the star. But rigid rotation added sort of around the z-axis as well. This is of course then calculated in the co-rotating frame of reference to make it static. But unfortunately, when you do a complicated potential as the one that you would need there, then you have to solve the differential equations numerically, which takes partially away from the advantages that I said that you could do a quick look thing. But it's again reasonably simple because it's linear equation and there are standard mathematical models that you could use. I don't know, even packages like MATLAB and so on. Okay, and I think this is the second to last slide. So one of the things that I mentioned when I talked about the potential field models was that we have an outer boundary, usually at sort of 2.5 to 3 solar radii for the global magnetic field models. And one of the things that has become a bit more important now that we have Parker Solar Probe and Solar Orbiter missions ongoing is whether one can kind of push this outer boundary out a bit further. And I mean, I phrased it here as can one remove the source surface? That only happens to a certain extent that one can remove one outer boundary, but one has to have another one. I mean, there's no numerical simulation we can really sort of push the boundary to infinity without losing accuracy, maybe. So here, this is in a paper again led by Thomas Wiegelmann, where we've tried to change or modify the optimization method to include field-aligned flows on top of actually gravity and pressure. So here, this is from a 2020 paper in solar physics again. So here we show a comparison. So the outer boundary here is 10 solar radii, I have to say. And what we show is on the left-hand side, or what I show here is a nonlinear force-free field extrapolation, which actually goes out to radius 10, which uses STO HMI data, synoptic vector magnetograms as boundary conditions, and the same on the right-hand side. But there's a sort of relatively simple Parker solar wind imposed. And one can see that the magnetic field there gets radial at a pretty close distance to the sun there. And one can also see this in the summary plots where the radial magnetic field is shown for this flow MHD thing. You see it's basically taken over all of the magnetic field here. That's a ratio of mod BR to mod B, whereas the nonlinear force-free one sort of has that tendency, but even at the outer boundary has not reached that. And this is kind of the difference between the force-free and the flow MHD magnetic field. Okay, I think I'll come to the summary now. So, so I showed a few examples, and only a few, and very selective, heavily biased towards my own work, obviously, of the use of plasma equilibrium models in solar physics. And one of the things that might have stood out, at least at the beginning, is that numerical methods are essential due to the nonlinear nature of the problem, especially in extrapolation, nonlinear force-free and MHS. But there are also possibilities for using analytical methods to complement these numerical methods. So it's not that, you know, we seek to sort of replace numerical methods by analytical methods. I mean, the numerical methods will always be superior in the detail if they're done correctly. But as I said, the analytical methods might have value in sort of having a, you know, if one wanted to have a quick look without doing sort of lengthy calculations, attention to all kinds of different things there, they might have value in a quick analysis of things. I've at the end also sort of touched upon that the methods for these analytical methods might be useful for other applications, for example, stellar magnetic fields. And the final point that I just made was, can we shift the outer boundary of magnetic field models further out? Maybe to include plasma flows. We've done that. So that model that I showed there didn't have any rotation. If we wanted to go further out, we probably would have to include some sort of rotation of the sun. We've actually done that, or started to do that already, but this I think we haven't finished that effort yet. Okay, that's it from me, and I'm happy to take any questions.